Hey everyone, happy Friday. A couple of, not really announcements, but just plugs, I guess, at the very beginning. There is the graduate seminar today, right after our class, the topic of which will be, it sounds like, one gentleman's journey through digital communications. So if you are a graduate student, I expect that you'll be there. But if you're an undergrad, I'd actually encourage you to go and listen for an hour. The link is in the email that Yvonne sends out every Friday. And if not to ask questions, then just to see actually after taking this course, how much more of what he talks about do you actually understand, or do you catch references to, or whatnot. So if you have an hour, I would suggest going and checking out the graduate seminar at 2 o'clock. The other plug is for EE416 in the winter quarter. So I am scheduled to teach what's called Advanced Digital Communications, and it's listed as a 500 level graduate course, but I would be happy to entertain anyone who takes this course to take that as well. If you are debating whether or not to take it, and the deciding factor would be what we're going to cover in that class, I'm open to suggestions. I've never taught it before. I have an idea of what we could cover, but if you'll only take the class if we cover X, let me know, and I'll see if I can work that in, because I'd like to see you there. Okay, other more logistical announcements. Homework or problem set 4 was set up Wednesday, so it'll be due next Wednesday. Problem set 5 has not yet been posted. When it is posted, you will then have a week to work on it, or at least a week, I should say. But we are now ready to move on to unit number or module number 6, which is all about spread spectrum. I'll pause here actually in case there are any lingering questions, anything I can help out with before we soldier on. There are, I exported the PDF note set last night, so it's available on Canvas for you to download now. Okay. So the order of events here is a little bit strange, and that's because most of the time when you take a class, I don't know why this is, but the classes that I've taken are normally ordered in historical order, right? You learn the things that were discovered first, and then you proceed chronologically through them. This is an exception. So spread spectrum techniques were implemented, at least in digital communications, before orthogonal frequency division multiplexing. So we are kind of going back in time, if you like. However, like I said, OFDM was a thing, was a known concept back in the early days of telecom. It just wasn't implementable practically. That's different than these spread spectrum techniques, which were put into practice actually as early as the 40s. And I think you'll see why in a moment. But I think we should first just have a quick overview about what I mean by spread spectrum. Up until this point, in order to send the most data through a physical channel, we have had a couple of different ways to do that. We can just say every bit or every m bits that come through, we'll put them on a symbol. We'll mount that symbol up to a passband carrier and send it through. That is fine if you have a low data rate or you have a low number of users trying to use the channel, the physical channel. When either of those things becomes not true, then it is more appealing to start using multiplexing type technology or technique. So we've talked about time division, so everyone gets their own time slot that you can do. You can use the whole frequency band in your time slot. We've talked about frequency division multiplexing, which is you can, everyone transmits all the time, but everyone is assigned a narrower subchannel, subband. And in the limit, if you like, We have orthogonal frequency division multiplexing, which is everyone gets sub-bands of sub-bands, and those sub-bands, those sub-sub-bands, are orthogonal to each other. So you can pack as much data as you can in these very nicely packed subchannels, and then different users will be given different resource elements at any given time to try and submit on or transmit on those subchannels. Spread spectrum is, if you like, an orthogonal method to all of these. So I mean that in the kind of colloquial sense. It is strikes off in a different direction. Time division multiplexing is pretty easy. You only have to worry about a certain segment of time, and you can be quiet for the rest of the time. Frequency division multiplexing, you can actually kind of understand it if you are comfortable with filters. Is that if I just have a band that I'm interested in, I can try and filter out the rest, and so that's fine. Spread spectrum is the idea that let me take my information, my data, and let's say it comes along at one bit every TB seconds. And rather than mount each of those bits, or m of those bits together onto a symbol and mount that symbol, rather than mount that thing onto a pulse and send that pulse, I'm going to mount it onto a pulse and then intentionally break up that pulse. I'm going to intentionally introduce oscillations into that pulse to take the bandwidth of the pulse and spread it out in frequency. Now, on its face, this seems silly because you're intentionally increasing the bandwidth of your signal. But the idea is there are reasons why one might want to do this. In particular, it is helpful in multiple access communications. That is, when multiple users are trying to use the same physical medium. If you spread everyone out in frequency, as long as you intelligently despread them at the other end, you can actually fit a whole lot of people in, or a whole lot of data streams in a finite time and frequency window. And the other benefit, and the reason that this was actually developed in the first place back in the 40s, was spread spectrum gives you the ability to transmit in the presence of jammers. We haven't talked a lot about RF jamming, but you can imagine that in the 40s, when radio was new, there was something else going on in the world where people wanted to block each other from communicating. And so pretty soon after radio communications were introduced in the 20s and 30s, we get World War II, and people are trying to jam each other from talking across the battlefield or across the Atlantic or whatever it happens to be. And so a little bit of a historical perspective. Do you, this is easier if we were in Building 20. There are all those pictures of old European men in the walls of Building 20. Well, one of them, at least one of them, is not a man. So there's a picture of Hedy Lamarr in the halls of Building 20. She was an actress in the 30s and 40s, but she's also got her name on a patent for frequency hopping spread spectrum. So she was also credited with inventing this jammer resilient form of communication during World War II. So that's, it's not going to be on the final, but I think it's an interesting thing to note. Okay, so as I mentioned, the whole idea behind spread spectrum is we take data that would normally live kind of tight in time and frequency, and we spread it out in frequency. There are two subtypes of spread spectrum that I want to talk about. There is frequency hopping spread spectrum, and this is versus direct sequence spread spectrum. Okay, so we'll talk about DSSS later, but we'll start with FHSS because it came first historically. This is what Hedy Lamarr has her name on a patent for. Okay, so the idea is take the data, and we first need to modulate it using our traditional baseband modulation techniques. So in this particular case, we're going to use frequency shift keying. And this is a limitation of FHSS, is that in order to do FHSS, we need to use FSK modulation. So let's talk about what FSK modulation would look like. Remember, it's frequency shift keying, so that means different symbols get different frequencies. So the idea is that the FSK signal, so this guy here, is going to be a cosine, and it's going to be a cosine for one symbol period. And omega m is drawn from a list of possible omegas. So omega m is drawn from a list that looks like, say, omega carrier plus or minus 1/2 delta omega, omega carrier plus or minus 3/2 delta omega, etc., on up to plus or minus m minus 1/2 delta omega. Right, so the idea is that the FSK modulator looks like a code book in that we take collections of bits and we say, oh, if it's a 0, 0, 0, then we map it to frequency 0. If it's a 0, 0, 1, we map to frequency 1. And those frequencies are enumerated in this list of possible frequencies. Okay, so for example, an m equals 2 codebook, FSK codebook, would look something like, if a 0, 0 comes in, then map that to omega c minus 3/2 delta omega. If a 0, 1 comes in, map it to that frequency. If a 1, 0 comes in, map it to this frequency. And if a double 1 comes in, map it to the highest frequency. Okay, just like in QPSK, if we had pairs of bits, they would each get their own phase. Here, if we have pairs of bits, they each get their own frequency. And so once the next pair of bits would come along, then we would change frequencies. Okay, that's not the frequency hopping. That's just normal, regular old frequency shift keying. Each symbol gets its own frequency. If I shift frequencies, then I've shifted symbols. That's where the name comes from. And then this could obviously be extended to m equals 4, m equals 8, et cetera, et cetera. And so the idea is that this is true during symbol period m, little m here. Okay. So the frequency hopping comes along when we change the frequency of this cosine, of this S sub FSK, according to a random sequence. And this is actually the key to why it's hard to jam and the key to why it's easy to despread. So let's talk a little bit about pseudo noise and what I'm on about with that. So pseudo noise, which I'm going to abbreviate to be PN, which is a little frustrating because it doesn't actually have a P sound at the beginning. But pseudo noise is simply a technical term for a random number generator generated by a computer. Okay, so this is where we have to start to differentiate between random noise and pseudo-random noise. Can anyone actually, this is a good question. Can anyone articulate the difference between the two? We got a chat coming through here. Yeah, so Jack says pseudo-random is generated from some pattern. And that's exactly right. Whereas truly random, there is no way, given the value at any given time, to predict what is going to happen with certainty in the future. Pseudo-random is actually, that's not true at all, is once you know the pattern, then you can predict what will happen at least sometime in the future. And this is the difference between a truly random event and a random number that's generated on a computer, which is a deterministic machine, right? There's nothing actually random going on inside your computer. What your computer is doing when you're asking for a random number is it's taking, well, I don't know what it's doing currently, but it used to take the value of the clock and put that through a whole complicated arithmetic operation. And because it would be sampling the clock at ostensibly random times when you click the give me a random number button, then what would appear would be a fairly random sequence. But at the end of the day, your computer actually can at best give you pseudo-random numbers because your computer is itself a deterministic machine. Okay, all of that is a roundabout way of saying is what we're doing here is we're generating roughly random sequence. So this pseudo-random generator is going to be giving us a string of random things, and we're feeding a frequency synthesizer with those random inputs, which is then being used to upconvert the baseband modulated FSK signal. Okay, so this omega sub h is drawn from a set of frequencies of size L. Okay, so that means that in some sense, the pseudo noise generator is going to be giving you values between 0 and L minus 1. So this guy is going to be integers, if you like, 0, 1, up to L minus 1. And then what the frequency synthesizer does is just say, okay, if you give me a 0, I'll give you frequency 0. If you give me frequency 3, I will give you, or sorry, if you give me input 3, I will give you frequency 3. And so what the frequency hopped signal then becomes is a frequency due to pseudo noise added to a frequency due to the symbol that you're trying to actually send. So representing it this way as the sum of two frequencies, then I hope it becomes clear that what we're doing here is by changing each of these frequencies, we end up changing the spectrum of the transmitted signal, right? In the kind of simplest possible case, we don't do any frequency hopping, and then we're just seeing the frequencies in our code book with a bit of spreading because we're switching between them. You saw that in the FM problem back in problem set number 2. If we switch between frequencies, then we don't get the two distinct frequencies that we're trying to, our message frequencies, we get a spread of them. But we're actually spreading intentionally more than that because we're adding in this changing frequency component, the omega sub h. So if we've got, and the reason, so this L is called the spreading factor. And so one reason it's called that is that if we have a bandwidth, so if we track the bandwidth along this diagram, then each of our symbols is going to have, say, bandwidth B sub s. But if we change the frequencies within this frequency hopper by a factor of L, then the bandwidth here becomes L times Bs. And so whether you change the frequency hop many times per symbol, or you have many symbols per frequency hop, you get the difference between fast hopping and slow hopping. So let's take a second to understand that. If I have my symbols coming along here, and this is the time axis, then I could have, say, symbol number 0, symbol number 1, symbol number 2, and each of these would occur, or would have the symbol period to be transmitted. Now, separate from that is the PN rate. So in the slow case, you'd have omega 0 here, and this would be what we call the chipping time, T sub C. Okay, so in slow hopping, we have multiple symbols per hopped frequency. And then, of course, the other way around is if you have multiple hops per symbol, we call that fast hopping. So I'll do this in a different color. And it would be, let's do, yeah, factor of 4. So this would be T-chip, 2 T-chip, 3 T-chip, 4 T-chip. So whether or not this signal changes at a rate faster or slower than this symbol data changes, we have either fast chipping or fast hopping or slow hopping. So I guess rather than just me drawing random lines, we're going to compare rate of change.
Do we never consider the case when the rates are the same?
If the rates were the same, that's essentially
just FSK.
Exactly, it'd be FSK, but kind of in 2 unnecessary steps, if you like. I think that also what you'll see is that we have more benefits with the fast hopping. The technical limitations are that you need a computer that can hop faster than your symbols are being generated. So I think that the slow hopping rate is kind of a historical holdover, if you like. Okay, so I think I actually have well, not a live demo, but at least something, a visualization. So BFSK, that's probably the first time we've used that. This is simply FSK, wait for it. No pen? Pretty please. So BFSK is just M equals 2. Binary frequency shift keying. And so my omega C would be 15, and my delta, well, we'll do it in hertz here. FC is 15, and delta F would be 5 hertz. So we're going from 15 either down 5 or up 5. So 1 bit means FSK to 20 hertz, and a 0 bit means shift your frequency to 10 hertz, which is why the wiggle gets slower here. So what I've got is L equals 4. And so my pseudo noise is going to be a random sequence of integers, in this case from 1 to 4. And so what I'm doing is I am drawing my, so these are from my frequency synthesizer. What we're going to say is we're going to add, when my pseudonoise is, say, 1, we are going to add to whatever the FSK frequency is, we're going to add 10 hertz. So I think what we've got here would be 20 hertz from the FSK plus 10 hertz from the frequency synthesizer. So this would be a 30 hertz wave for this small period. Let's do the other one. So in here, this is going to be the 20 hertz from the FSK plus the 40 hertz from the synthesizer. So this would be a 60 hertz wave. And then you do that for every pseudonoise sample and for every symbol. Okay, so this is an example of fast chipping where you're doing it 4 times. Yeah, so here's our symbol period. And I'm chipping multiple times, or sorry, hopping multiple times within each symbol period. Slow is it's easier to write because you're doing fewer hops, but it's still important to see that if your if your data changes within a hop, then the frequency still changes, right? So even though we're only adding 20 hertz in this region, we still have to respect the fact that the data symbols themselves are changing from 10 to 20. So that means this would be 30 hertz and 40 hertz. Okay, so we actually haven't showed anything in the frequency domain yet, but I hope that you're going to see that by changing the total frequencies in the signal that we're sending, we should be seeing spectral content appear at places that it otherwise wouldn't, right? Especially comparing this picture to this picture, right? There's lots, in addition to being more wiggles, there are more different wiggles. But the same statement can be made here, that there are more different wiggles. Sandra?
Could you clarify how you got the 30 and the 40 hertz at the bottom waveform?
Sure. So this 30 is 10 plus pseudonoise sample number 2. So 20 from the pseudonoise and 10 from the data.
Oh, gotcha. Okay.
Yeah, the 40 is 20 from the data plus 20 from the pseudonoise. And I 20 because I'm just mapping pseudonoise sample to frequencies by a factor of 10. It doesn't have to be like that, but it's just every pseudonoise sample changes the hopped frequency. Okay, so I ran an FFT on this, and sure enough, if you just look at the spectrum of the FSK signal, there were 3 1s and only 1 0, which is why these 2 peaks are at different heights. There were more 1s than 0s, so the frequency corresponding to 1s has more power than the frequency corresponding to 0s. But there was, and this sideband stuff is mostly just due to FFT leakage. But when you start to talk about the fast shipping, well, then we've got the same power, but it's distributed across lots of frequencies. Like, what the hell's going on here? It's really hard to tell where the power lies, where the energy of the signal lies. And that's precisely because we are spreading the spectrum, hence the name. Okay. We're also spreading the spectrum when you do slow chipping, but it's less spread, okay? Because we had, here's your 30 hertz stuff, here's your 40 hertz stuff, here's your 60 hertz stuff. This was from the first 2 data bits, and these were from the last 2, like we just said. So if you let this go on for longer, then you'll have more peaks at the different possible permutations of message frequencies plus hopped frequencies. Okay. The more frequently you hop, the more spread you get. Questions on this? I think this is, I mean, it's not a live demo, but I think it illustrates the point of where does the name spread spectrum come from. We haven't talked about how to recover, right? So if your transmit team is sitting on one end of the building and your receiver design team is sitting on the other end, and the transmit team says, look, we're going to give you the spectrum and we want you to decode it, the receive team is going to be like, which is why you have to work together. Ricardo? Was that a question?
Sorry, no, I just unmuted accidentally. Sorry.
Oh, no worries. Okay. So we'll cover how to decode from this in a bit. But this is a good time to introduce this idea of jamming. Really, it's only relevant in RF, kind of open wireless. I can't think of an opportunity to jam on a wireline communication, but probably someone more nefarious than I have thought of a way to do it. So one way to represent jamming is in the frequency domain to think about if you are transmitting your data. So it's called signal spectrum, but this is say your data, the power spectral density of your data. And say the jammer knows what frequency you're using, then he or she can deploy their RF energy into your band, and we get essentially what acts like extra noise in that band. So the idea is that the jammer wants to contribute to the noise so that it makes it harder for you to decode what you're sending, hence jamming. On the other hand, if you're using frequency hopping, then what you end up doing is, like we saw on the previous slide, you end up allocating your RF power onto many different bands. And if we assume that the jammer is power limited, and all that is to say is that the jammer has a finite amount of power that he or she can use, which I think is not a terribly wild assumption. Then in the narrow band case, the jammer is free to put all of that power on the one band that you're using. In the frequency hop case, the idea is that this rectangle has the same total area as this rectangle to represent the same amount of power. And if you're sending your signal across lots of frequencies, then maybe the jammer can try and follow you around, but in the best case for you, the jammer just transmits their power over all the frequencies, and you are free to pick out your data at the other end. Because what's not represented in this picture is that there is a time variation component. Right? Because you're frequency hopping, you're first going to put your power in this band, and then you're going to put your power in this band, and then you're going to put your power in this band. But if the jammer doesn't know the order in which you're hopping, the best the jammer can do is to jam everything, but that ends up diluting his or her power, and so his or her jamming is less effective. You follow that? Now, let's say the jammer wants to try and outsmart you, and they say, "Oh no, we know that they're going to transmit at this frequency sometimes. They're going to transmit at other frequencies other times, but let's just put all our power here." And you know what? They're right. They are probably going to be very effective at jamming that frequency, right? Because they're going to appear as additive noise on that frequency. But these guys are free and clear. So this is a motivation. If you're very security conscious, if you're jamming averse, what you'd like to do is you'd like to maximize the number of free and clear subchannels you have, which would mean you have to maximize the spread of your spectrum. Yeah, so I think the key to understanding this slide is to understand that we are collapsing the time domain. So if you were to actually explode this slide out and introduce a time domain concept, the jammer is jamming like this, and then you're here. And then for the next symbol, the jammer is still like this, and now you're over there. And then for the next symbol, the jammer is still spread over there, and then you're over there. But if you were to collapse these together, sorry, other way, then you would get this picture. Okay, if you were to smush the time domain together. So can we see how, any questions about how this gives us an advantage over jammers? Ooh, critical thinking. When would it not? When would everything I just say not be true? When could the jammer do just as well in spread spectrum as in narrowband communication? Right, you have to know your enemy. You have to think like your enemy. If you're in a low SNR situation, then, so yeah, so Jack says in the chat that if you're in a low SNR situation, and what we're not displaying here is actually the ambient noise. But in a white noise model, there's going to be, for high SNR, you would have kind of an ambient noise. So high SNR additive white Gaussian noise. In a low SNR, then all of a sudden that baseline gets put up here somewhere. In which case, it's going to be hard for you to communicate even without the jammer. And the jammer is going to be able to perhaps even not jam if they know that you're in a low SNR situation. And then maybe the jammer can then save up power and then jam more later times. Yeah, I like it. I think that's a good idea. The other instance is if the jammer knew your hopping sequence, right? If you had an intelligence leak, which is what I call second year of EE, no, come on, no one smiles. You people. If you had a leak and the sequence over which you were hopping was leaked to the jammer, then they could just follow you around the spectrum, and then you'd be no better off than you were before. Yeah. So that is motivation for one, keeping your hopping sequence secret, but two, keeping your hopping sequence difficult to guess. Yeah. So if your hopping sequence is just hopping between two things, then all I have to do is try one of those two things, and I'm going to get it 50% of the time. But if your hopping sequence is long or difficult to guess, or the periodicity of it is long, then you have insured yourself against someone getting a lucky guess who is trying to jam you. Let's see, what else can we talk about? If you have multiple people, and these are, now we've moved away from jamming to just say, let's say we've got multiple users, and these users are just trying to get their data across a common channel, and each of them has their own hopping sequence. Okay. So no one nefarious here. No one is trying to block anyone else. Everyone's just trying to get their information from A to B, and they're happy to be using the same physical channel. If you use a frequency hopping scheme, then it's possible that for certain chips, many people, more than one person, will try to use the same frequency. And so I think this is actually an animated slide, but should we try that? Yeah, let's live dangerously. Wait for it. Huh. Is there a big black box in the middle of your screen?
I do see the slide.
Okay, sweet. So let's say there is the gray user who has some frequency hopping schedule that looks like this. So at every chip, they're hopping from channel 5 to channel 1 to channel 7 to channel 1 again, et cetera, et cetera. And they are the only person in the world, they're the only person using the channel, and they're happy. But then user 2 comes along and says, I would also like to use this physical channel. I am going to hop from channel 9 to channel 7 to channel 4. I just realized I've been using the word channel to refer to different things. There are frequency bands that I'm calling frequency channels here. And then there's like the physical medium, the system by which you're trying to transmit your data, which I'm trying to call the physical channel. But this is actually a pet peeve of mine amongst communication engineers, is that they use the word channel to mean pretty much everything. And if you're not careful, you can get confused. Okay, so we're using the same physical channel, and we're opting to hop between frequency channels. And then a green user comes along, and they're going to hop from 8 to 6 to 3, et cetera, et cetera. But you can see that at any given time, the more users that I have in the physical channel, the better my odds of collision are, or the worse my odds of everyone getting their data through clearly. Because I think when I add purple, we get a collision right here because purple collided with gray, I think. So this is a problem when everyone is in control of their own frequency hopping scheme and there's no coordination between users in a physical channel. Okay, that's really all I wanted to share here. Can we get out of there? Okay, so there ought to be a way to accommodate multiple users of a physical channel with trying to minimize this risk of collision. And that is actually what gives rise to the sequel to frequency hop FHSS, which we're going to call DSSS, Direct Sequence Spread Spectrum. Direct Sequence Spread Spectrum. Yeah, that's legible, sure. That actually would have been a really good place to pause for the day. And so I actually think I'm going to pause for the day. We'll come to DSSS on Monday. But yeah, I'll hang out here until my time is done if you have any questions. But otherwise, I think that that'll do it for today. Thank you.